Brett.
We're co-talking. All right. Cool. Welcome everyone to MySec Southfield. My name is Brett Hansen. I am the Southfield director. MySec meets in 5 locations: Jackson, Lansing, Detroit, here at Southfield, and Grand Rapids. Other organizations, if you're interested, is ISC Squared, North Oakland ISSA, Motor City ISSA, and Lansing ISSA. We're currently meeting at Town Square Food and Spirits. Please pass your thanks. Make sure you close out your tabs if you haven't already. Also, thank you to Tech Systems for providing food and snacks. If you guys aren't already, be a part of MySec. If you have a topic for a talk, talk to the real Brett. Next month, we are looking for someone to do a AppSec talk or for OWASP. So if you guys don't talk, I'll probably have to do it. So please. Other announcements. The social this month is Thursday the 25th at One-Eyed Betty's at 6:30. Converge Detroit is in 34 days, May 16th to the 17th. Also, there's Circle City Con starting May 31st to June 2nd. Are there any other announcements?
So we've been meeting at One-Eyed Betty's for a little while. We mentioned that we'd go through the spring, so keep an eye out. Probably sometime next month we'll put it up for a vote to see where the next social will be, probably for the summer. If you want One-Eyed Betty's, vote for it. If not, throw out some suggestions so we can put that into the pool of places to go to. Cool?
Sounds good.
Okay. All right. And with that, we'll hand it over to Sam.
Evening, everybody. Tonight we're going to be talking about dynamic taint analysis using live DFT. So I'm going to start off tonight talking about my favorite subject in the entire world. And then from there, we'll talk about what DTA actually is, why it's useful, talk a little bit about the tools that will enable us to do it on the Intel platform, a brief overview of how we're going to actually pull it off, and then we will see it in action. And finally, a few methods you can use if you're a software developer to evade this particular technique and throw off anybody trying to reverse engineer your work. So, who am I? My name is Sam. I'm a software developer who's working currently in the identity management and auth field. The way I got into this particular subject, I'm studying reverse engineering right now. I originally got introduced into it from some time ago from a preservation standpoint, particularly for software platforms that were closed, relied on servers that weren't available anymore. There's a lot of cultural experiences out there which are slowly eroding as the support ecosystem goes away from them, and it's people who are reverse engineering them that are making sure that we can keep experiencing those into the future. It's only more recently, as I got involved with MySec, that I got involved with looking into commercial applications for reverse engineering, such as malware analysis, closed source products where the code has been completely lost and somebody needs to keep supporting a product for it. And since we're doing this as MySec, that's what this talk is going to focus more towards, is those kinds of use cases. So, what is dynamic taint analysis? At a high level, it's basically a data flow tracking technique. So it's going to be within a single binary. We're going to be looking at data that's coming into our programs. We're going to automatically track it as it's moving through the binary. And that's where our tools are going to come in with Intel Pin and Live DFT. And then we can mark areas where we care about the data flowing back outwards. So that'd be our taint sources is inwards, taint syncs is for the data that's flowing back out. All right, so why are we going to do this? I kind of touched on it a little bit already. If you have a closed source tool where you want to know how does data flowing in affect my outputs, or where inside of the program is it going, you have a couple different options. The most painful way that you could possibly do it is you could manually reverse engineer it and go through function by function, track every byte as it's going through, and just manually try to build up a graph of where things would go. This saves us a lot of time with that. If you can just mark a few areas where you care about ingress and egress points, then have the framework handle it for you, then that'll speed you up by orders of magnitude. Another one is if you're looking for information leaks. If you have a system where you want to be absolutely certain that a bit of data, let's say your private encryption keys, never gets transmitted outside of it, then you can mark that information as tainted, set up a taint sync for it, track that, and immediately flag it, whether you want to shut it down or if you're in a testing environment, you need to actually fix the code once it's gotten that far. Data flow in general is also used by a lot of software development tools to implement optimization, basically tracing through, and if data never reaches a certain area for one reason or another, then you can make a more efficient version of the program that's just not going to have as many instructions running and therefore will execute everything a lot more quickly. All right, so let's talk about Intel Pin first of all. This is a instrumentation framework that you can run on any arbitrary program that you have. Typically, if you have a instrumentation kind of tool set, you're either going to be looking at a specialized compiler, and the problem with that is you are needing to have the source code for that. You have to compile your program in a completely special mode. It's fine if you're developing the system that you're trying to test, but if you are in one of these situations where you have some malware and you're not sure what's going on, or you're trying to audit any kind of tool that you did not write, then obviously the compiler mode is not going to work. The other method that you could use would be an emulator. Problem with that is you're looking at several orders of magnitude in slowdown using a CPU emulator framework. So Pin, what that's going to do for us instead is it will be injected directly inside of our process, and then it's going to act as a just-in-time compiler for the entire binary. What that means in lower level terms is as every function is executing for the first time, it's going to take in the original version of the function, it'll analyze it according to a set of rules that we define, or whatever our instrumentation rules are, and it'll emit a new version of the function that executes both the original program and it runs whatever our rules were. Benefit to that being you're looking at slowdowns more in line with about 30 to 100% as opposed to 30 to 100 times slower. It is used commercially by Intel for a number of their products, including Intel Parallel Studio, which tracks to see if your code is thread safe. There's several other tools they have that they'll sell you for thousands and thousands of dollars, where Pin is the underpinning for all of that. And then we have LibDFT. This sits on top of Pin, and this is what provides the actual taint analysis aspects of it. Basically what it does is when you go to compile your Pin tool, it provides all the logic that understands how the CPU works, and basically says if this operation is working on this part of memory, we need to mark these areas as tainted, and keeps track of all that information for you. Without this, you'd be looking at hundreds, maybe over 1,000 different Intel processor opcodes and having to manually re-implement every single one of them inside of Pin, which is clearly not ideal. The nice thing about it is, too, it is open source, so if you do run into a hole with LibDFT's implementation, of which there's a few that we're going to discuss a little bit later, then you are free to patch it, distribute a revised version of it, do whatever else you need to with that. And while it is fast, you have to bear in mind it's not foolproof. If you've looked into commercial reverse engineering applications at all, especially with malware, they'll often do anti-debugging techniques. They'll look for tools that people use and try to thwart those, maybe shut down early, not execute certain bits of code. And since we are running in the same thing that we are analyzing, we're vulnerable to all those same kind of techniques where the author of the code that we're looking at might throw in a countermeasure against us. But we'll go into more detail about that later on in the talk. Okay, so let's look at what our actual strategy is for implementing this. We're going to be starting off with a taint source. These are C functions that we write ourselves to define them. And it's basically any data that we're looking at that we care about where it's going inside the system. Frequently, it'll be untrusted user input if you want to see what in your system can be affected by, say, network communications, configuration files that might be overwritten by a non-savvy user, let's say. It could also be your private data. I mentioned earlier about private key files, so we can track those as well. If you are taking a project where you're trying to find out what did the server actually affect inside of it, then this could be your opening point for seeing what those network comms were doing as a first step with some of your reverse engineering work. Typically, we're going to do these at I/O boundaries or OS system calls. So for instance, every time we're reading a file and so on. But you have the option of also hooking in the middle of a function. So you could say every time we do a jump instruction or a call into a function, then depending on which function it is, mark certain data inside of there as being tainted. Oops. Did I just skip 2? Nope. Okay. All right, so now that we've defined our taint sources, we're getting into the areas that LiveDFT is going to be automatically handling for us. So what we have here is we have to have somewhere inside of the process to track what data is tainted, how, and LiveDFT refers to this as shadow memory. It's basically a different part of your process's memory space where we're going to be storing all of this information. And we have a couple trade-offs that we have to make when we're implementing shadow memory. One is how granular we want to be. You could go as low as tracking every individual bit, whether it's tainted or not. You can go to the byte level, memory page, or word of the processor. With LiveDFT, it's going to be using the byte. So it's about as granular as you can sanely get without doing a whole ton of extra overhead for no good reason. So for every byte, we're going to have to be storing a little bit of extra information somewhere else. Now, the other trick we have here is we have to decide how much taint information we want to store. If we only have one source of it, and it's just a strict matter of on-off, then we can store things in a bitmap. So for every byte, we're going to be storing things in a single bit. Is it tainted? Is it not? But for a lot of applications, especially with what we're looking at tonight, you're going to be looking at wanting to track multiple sources. And for that, LiveDFT allows you to do a full byte for every byte. So you have 8 bits inside of each byte that allows you to track 8 separate sources of information. Now the thing you have to remember is because all of this is running in the same process as you are instrumenting, you're looking at very quickly doubling your memory usage. And if you have a high memory using process that's, say, 32-bit, where normally you'd be looking at 4 gigabytes of address space or 2 or 3, depending on which version of Windows you're on, that's going to be cut directly in half. You're using the same space that your program needs to track everything. So you want to carefully consider whether you're going to be looking at strictly or multiple sources like that, or if you can get away with just using bitmaps. Anybody have any questions so far? Okay. Okay, so taint propagation. This is, like I mentioned, the really painful part where we're really going to be leveraging not just PIN, but LiveDFT's knowledge of the processor. So what they've done is for every processor instruction that you'd be looking at, they've manually written in logic saying, if this is in that function, then you need to emit some instrumentation code that will modify shadow memory accordingly. So for instance, if you have the exchange instruction at the top, we have one untainted byte being swapped with a tainted byte with value 1, or which I've chosen to mark as red throughout the duration of this talk. And then at the end of that function, it's just going to swap the shadow memory that corresponds to each of those 2 bytes. Similarly, if we have at or move, it's going to be completely overriding the destination byte with whatever our source byte was. So it will also be overriding whatever our destination byte's taint was as well. So we had a byte that was originally tainted with value 2, it could have been 0, whatever else, and it's just going to be completely overwritten, or other way around. It had 1 originally, it's going to be completely overwritten with 2 there. Now what gets really interesting is when you have an instruction that looks at 2 bytes as the source, that each have different taint values. And so in this case with add, we're going to be taking both the 1 and the 2, and we're going to be mixing them together and flipping both bits on in the destination. And that's why even though a byte could hold up to 255 values, when we're doing multicolors for our byte tracking, we're only going to be storing up to 8 different sources of taint. Because that way we can track as they're mixing together. We can say, oh, this bit of information was both affected by the network and it was affected by the configuration file. Or this one was only affected by the network, and that helps us more quickly narrow down things in a complicated system. Ryan.
This could just be my misunderstanding.
Yep.
In the exchange operation,
Uh-huh.
it looks as though our tainted byte is OX01, which is going to be exchanged with the OX00. So on the right-hand side, am I wrong in assuming that OX00 should actually be colored red? Or do those not represent the memory addresses, those are just values? Like, do you understand what I'm asking?
Yeah, so those are,
Tracking the value.
yeah, anytime you see a byte with a hex value in this talk, it's going to be referring strictly to whatever the taint value is.
Okay.
Yeah.
So in this situation, the blocks themselves in the positional order represent what they were on the left-hand side.
Yeah, I avoided putting in memory addresses because having too many hex values on the same block was just going to become busy, and it really doesn't matter what the addresses are. These could even be registers.
Understood.
Yep.
So just for re-clarification, you're not tracking the memory space, you're tracking the value.
Yeah, or where it came from.
Okay.
Yep. The shadow memory does care more about where things are. It's going to be using offsets of the memory location to look up where things are inside of itself, but that's outside of the scope of what I'm showing in the graphics. All right, and then finally, we're going to be defining whatever our taint sinks are. It's pretty much the inverse of whatever our taint sources were. It's still a C function where we can do whatever we want. So that could be anything ranging from just writing a log message and continuing if we saw something interesting to shutting down the entire program. Or you might even do a memory dump or call in a debugger to take a live look at whatever's going on. If you were willing to pay the performance overhead, you could theoretically use this to say, hey, we're about to leak my private key. Let's just shut that down right away and stop the process. And most likely, you're not going to wind up doing that because any amount of overhead with the software development industry, regardless of what safety it introduces, has been discarded in terms of keeping things fast. All right. So is anybody familiar with a little-known bug called Heartbleed? All right, that's a unanimous no. All right, so as a refresher for those who aren't fond of remembering 2014, Heartbleed was a bug that affected a few obscure websites on the internet, wherein you could talk to an OpenSSL implementation, which would be running your encryption for your entire server, and they had a heartbeat message in there. And basically what this did for us was you could say, hey, I've got a little bit of data here. Can you decrypt it, re-encrypt it, send it back to me? And that way we can verify, A, that the connection is still working and that we're talking right, nothing's getting garbled. And B, it would act as a keep alive message for servers that needed to periodically be sending data in order to keep a connection going. Now, standardly, you would include an arbitrary payload and you would include a length. And you would say, hey, I have a string, hello world. It is 12 characters long. Please copy that data back to me verbatim, and I will just verify that. But OpenSSL had an issue where it would trust the client to tell the truth about whatever the string length was. So if I were to say that I have a string, hello world, and I was to say that its length was 65,535, then OpenSSL would diligently take that input, it would put it in memory, and then it would start at the beginning of my string and copy back 65,000 characters to me of arbitrary stuff. It might be somebody's login credentials. It might be your credit card information. It might be the credentials for something deeper in the infrastructure where I could do something even more fun. But because every time I send a message to it, it's putting that heartbeat message somewhere random, if I was to just keep sending messages over and over and over again to OpenSSL, I could slowly map out anything that was available inside of the process space and do pretty much whatever I wanted with that. And as you can imagine, this caused a few minor flame wars in some corners of the internet of people blaming developers about it. But the fact is, this bug was introduced and it stuck around for 2 years before anybody caught it. And it just happened to be one red team group that decided to test some infrastructure and said, hey, we found this bug that's been hanging around and half the internet's affected by this thing. So let's do a thought experiment here. What if we were in an alternative 2019 where that group never decided to do that red teaming, and this bug is still in the wild, unknown to anybody except for maybe a few agents at some Five Eyes agencies? So let's see if we can just use dynamic taint analysis and build an automated framework in order to find this bug without actually knowing about its existence. Okay, so we need to define our taint sources first. Now in this particular case, what I'm going to do in our hypothetical is I'm going to look for bugs where the private key could be leaked and sent out to the network. Because the OpenSSL Heartbleed bug could have affected any bit of memory, eventually if you run it enough times, you are going to find whatever memory the private key is sitting in, and it will get sent out. So for our taint sources, I'm going to mark two different areas. One of them is the client traffic that's coming in, and the other of them is the private key itself. So for those, I'm going to hook all of our read syscalls for the private key file, and basically anytime it's doing any kind of I/O with the disk, I'm just going to say, hey, if it matches up with what my private key file name is, mark that as tainted, and no matter where it goes, flag that with our red color up here. And we're also going to be tracking all of our network traffic as inbound, and we're going to mark that as tainted. Now in this particular case, I don't actually care about what's going on with the client traffic. I don't care where inside of OpenSSL it goes or anywhere else inside of my program. But you'll see why when I pull up the propagation slide and how libdft sees the view on things, why we actually have to have both of these sources in here. All right, so when we establish our OpenSSL connection, the first thing that's going to happen is the client is going to take the public key for our server and it's going to encrypt the session key for the rest of our communications and send it over to us. And the reason it's doing that is so that only us with the private key can decrypt that. That's how we establish a connection over a completely untrusted network and still avoid any kind of man-in-the-middle attacks. When we decrypt that with our private key, it's going to take on the taint values from both the client markings that we're doing and the private key, and the decrypted version of the session key that we're using for the rest of this is going to be marked in purple. And what that means is all of our client traffic that we send back out to the user, or any traffic we send back out to the client, I should say, will be marked in purple by the time it goes over the network. Now the reason that's important is when I was first setting up this slide and I was trying to figure out, okay, how would we watch for that? The intuitive thing you do is just invert the taint sources when you're writing the sync function. If I was able to monitor all of the network traffic going in for my tainted values, then surely I could just hook the same network traffic at OS call when I was going back out, and if it showed up with any red values, then we're good to go. But by the time the private key would have been sent back out to whoever we're talking to, it's already going to have been processed by our session key, and it's going to be marked as purple. Completely indistinguishable from any other traffic, so we're going to have to define our taint sync in a different location. So what I'm going to do instead is we're going to mark our taint sync as being at the point where OpenSSL encrypts all the traffic that's about to go outbound. And it'll inspect every single byte that OpenSSL is about to operate on, whatever was passed in. And if it's marked as purple, then that's something that just came in from the client and was already processed earlier. I don't care about that. They're allowed to see it again. There might be some other bug in there, but for the purpose of what I'm hunting for, it's irrelevant. But if I only see taint value 2, which is going to be our private key. Then we found the exact kind of bug that we were concerned about. Just shut everything down if it's in a production system. If not, take a full memory dump so we can find out what happened. Now, we're only going to see this particular case if the Heartbleed message happened to line up next to wherever the private key was stored. So that could be thousands, millions of iterations. Anytime you have this kind of automated kind of test, then you're looking at a lot of runs before you find what you're looking for. You can't just run it 2 or 3 times and say, okay, it was good. Everything's all set. Now, there is still one flaw in the methodology that I set out, though. When I set this whole thing up, I said that we were going to find the Heartbleed bug without having any knowledge of it pre-existing. And this scenario is still not going to happen if we have a well-formed heartbeat message where the length matches up with whatever the actual payload was. So for this, we're going to need some really, really cutting-edge 1989 technology, kind of stuff that your average software shop is still not caught up with, and that is what a fuzzer will do for us. Now, if you're not familiar with a fuzzer, it's basically a randomized generator for your data. You could do completely random streams of data, but most of them at this point, we're going to set constraints on them. So for instance, to send a message that OpenSSL will read it all, we might have to put in a checksum value, set a header in all of our messages, etc. But once you've set the few fields that have to match up with certain circumstances, you can put whatever else you want in the rest of it and just see what happens. It might be theoretically invalid, it might be wrong according to the spec, but as long as the server will take it in and communicate with you in some way, then I'm perfectly willing to send it garbage and see whether it does what I expect it to or not. And eventually the combination of the fuzzer sending a incorrect length value and the taint propagation putting it next to wherever the private key was is going to flag this bug, and it's going to just stop it red-handed for us. Originally, fuzzing was used primarily just to find crashing bugs. They'd use it on Unix tools and the like, but if we combine it with a taint analysis workflow, then there's a whole new class of bugs that we can build automated testing frameworks for and find without having to do manual code review. All right, so let's talk about this from the other side. Let's say I'm a malware developer, I'm a red teamer, or I'm developing some sort of copy protection software where I don't want somebody just wiring up a tool this quickly and tracing everything through my entire system without having to manually do some work. I mentioned earlier that LiveDFT, like any other tool, is not foolproof, and there are a few silver bullets that we can use to throw off a unwary engineer who doesn't notice what we've got going on here. First one is there are some instructions that LiveDFT has not implemented for us, especially, say, the MMX, SSE instructions are from the Pentium era. They were used for a lot of media operations back in the day, but most general purpose programs aren't going to be using them. Compilers are going to maybe shy away from those. So we can drop down into any inline assembly that we want to, implement those, and our trail is going to be lost pretty much immediately at that point. Another method, I was not able to find this in the literature. However, if you put it on the GPU, Intel Pin only understands the x86 processor. It doesn't know how GPU shaders work. It doesn't speak CUDA or OpenCL or any of those languages. So if you write a small kernel on there and you do nothing more than just echo the data back out or do a few minor operations on it, that's another way that we can lose track of it. Now you might choose to manually override some of these operations. You could implement a taint source that says anytime that we call into OpenCL or CUDA, then mark that data as tainted as soon as it comes back out. You have to explicitly do that and know that it's happening, first of all, so that's one way that it might slip past you. Another is that you can very easily get to over-tainting with that, where if only one tainted byte went in out of 10,000 and suddenly you're marking the complete output as being tainted, then you have a lot more data to sift through that's maybe not relevant to your actual use case. The other methods we have, one is you can corrupt the control flows. We are sitting inside of the process that is trying to monitor us, and we are free to do whatever we want if we notice that. The shadow memory is nothing special from your point of view, so if you somehow manage to detect that pin is sitting inside of your process and you follow through with the data structures, you can just overwrite all of them with zeros, and suddenly there's no data on anything left on you anymore. You can do other techniques that have also been used with typical anti-disassembly techniques. Say, jump into the middle of a complete instruction and execute something that would not have been detected by a pin when it was initially compiling your program again. Or, instead of putting hard work and actually working to avoid things, we can just do something stupid and write a loop that just starts a variable at 0 and increments it until it matches the exact value of whatever the tainted byte was. And as long as you fill the loop body with something that looks like it's actually relevant to your workflow, whoever is analyzing your program will probably not catch on to what you're trying to do here. It'll just slip by completely undetected. There's been some research into trying to avoid this particular problem and basically saying, if you have anything that's affecting the loop condition like this, then it should also be marked as tainted by the source. But in practice, what they've found is that it quickly leads into an explosive effect where half of your program is marked as tainted and all the data becomes completely useless. So any of the commercial grade implementations that we have now don't do that. So you have a very, very simple out. If you are trying to get around this as the reverse engineer, you're just going to have to manually annotate those areas, maybe do a little bit of rewriting of the binary to do something that'll match up a little bit better. And in particular, the reason that works, if you don't see it, is when I went over the taint propagation slides, every time it's running an opcode, it's looking at directly the source bytes in order to see how it's affecting the destination. But every time we're incrementing y by 1, we're not reading the value of x. It's just an increment of y that happens to stand alone from any checks of x, and that's why it's not able to check it inside of pin. All right, so that's all I had planned for the evening. Does anybody have any questions about anything? Ryan?
You said taint.
I don't understand why that's funny. Could you explain in great detail to me on the stream?
Sure. Will you go back one slide for me?
Yeah.
You repeat the question?
So I understand why you wouldn't be able to just look for the for loop, because then half your code just becomes tainted, right?
Absolutely.
But why couldn't you, and you're obviously would be better posed to answer this, like why couldn't you look inside of the for loop and we see that it's incrementing y by 1 until it's less than or until it's equal to x, look at that and then just run with the presumption that x is a tainted value and look throughout the rest of the code and see if we find that x value in other places.
Okay. So when you ask that, are you asking about from the perspective of the writers of libDFT implementing the logic, or as an individual reverse engineer trying to track this particular program?
Whichever one makes me sound smarter.
Okay.
Good answer.
So for this last case with the loop, if you are a reverse engineer who's tackling this particular loop and you notice like, hey, this is actually relevant, I'd like to keep track of that, then you could implement your own taint source logic that says anytime we're doing a function call, if it's this particular function that I know is bad and is trying to fool me, then like manually implement this extra rule on top. Of course, if they're doing that a dozen times, you're going to have a dozen different extra rules to write, and it's going to have to insert that everywhere. When it comes to a more general purpose case where libDFT detects these things for you, I'm not aware of anything in the literature about whether they have tried to do something like that or not. I would guess that there is a trade-off with that where that's a deeper kind of analysis and you would implement a much higher runtime cost in order to detect all of those. That's assuming that they can make it workable in the general case anyway, and that it's something that wouldn't lead to more of a over-tainting issue.
So when you were doing all of your research, is that even reasonable? Like, do you see that tainted value showing up in other parts of the code, or like anywhere where you could reasonably look for that value to be repeated? I don't even know if that question makes sense.
It probably makes sense, but I'm not understanding it enough to respond to it intelligently. Could you try to rephrase?
So essentially what I'm asking is like, so we know but don't know that X is the tainted value, right? We know it because we see it
Yeah,
here.
you and I know, but
Right.
it doesn't know.
Well, we don't actually know, but if we know that a common pattern that gets used that is hard to detect against is to set X to the tainted value and Y to 0 and to increment Y by 1 until we reach the tainted value, we operate under the assumption that in any of those scenarios we'll let X be a presumed tainted value and then look through the rest of the code or what have you for repetitions of that tainted value.
Yeah.
And then using that, maybe we flag that. In your research, did you find that, or is that just completely off base?
I didn't find anything like that. There were several papers I read, and it basically always came down to if you try to tie too much into the loop conditionals that way, then you wind up with issues in the general case.
Okay.
And I assume this is just one special case of the particular issue that they were running into, or else they would have put in something like that
Right.
overall.
Do you know how this differs from Geiger, the NSA tool that was just released?
Gydra?
Yeah.
Or Ghidra, however you want to say that. The G is pronounced the same way as it is in that graphics interchange format. So they're kind of complementary. I've messed around a little bit with Ghidra just to go through a couple crack me's. So Ghidra is more of like a high octane disassembler framework. So it can go through and it can show you the disassembly for everything inside. It can try to annotate things and even show you a decompiled C view of what's going on. But that is completely static. You're only looking at whatever the binary was able to show when it's not in runtime. It doesn't even have a debugger interface right now. And even if you had something like GDB, which I believe IDA Pro is able to hook into for its debugger interface, somebody correct me if I'm wrong on that. It's really going to be looking at things like executing the instructions, setting breakpoints, and stopping at certain points. But it's not going to be tracking all of your data flows through everything. They're very complementary tools in that regard, though. Like, I might do a first pass with Ghidra to find some interesting functions, and then I might write a few pin tools that will track taint through things, and based on what I find from that, I might look further into a few areas with Ghidra at the program. So it's just two complementary tools that don't really accomplish the same task in the end. Anybody else? Going once? All right. Thank you, everybody.